I'm Maurice Woods. I'm these three guys' mentor. Dylon, Mitch, and Corey have been working on several models for modifying coil and railgun, which they will talk to you about here.
So I'm Neal. I'm Dylon. I'm Corey. And our focus is on the most efficient linear Accelerator. A demonstration which is involved in the concept of the railgun engineering form.
All right, so this, see if we can play it. This is a model of a railgun. As you can see, current is being passed through the rail, going through the armature and then going back down. This electric current produces a magnetic field on the rails of the armature. Now, because the current is going in the same direction, the polarities of these fields are all at the same point. The like polarities are colliding. Now, when like polarities collide, they repel each other. Thus, the thing that can move, the armature, is at the end of the rail.
What we have here is a diagram of a coil gun. Well, a coil gun is an accelerator that uses coils, and when you use a capacitor, the discharge, the pulls through a coil and moves the projectile through the coil. When the projectile gets almost halfway, the coil shuts off, and when right after it turns on, the accelerator even more.
So our purpose was to see which type of electromagnetic linear accelerator, a railgun or a coil gun, was more efficient. So our hypothesis is that if we build two 6-inch models of each gun, and we keep other variables constant, the coil gun will perform better.
All right, so our method. We start off with initial testing using very small models to get the ideas of induction, magnetism, the electric current down before we build our small-scale models. These were 6-inch designs of our coil and railgun. Then we'll do several before they finally work. But once we have the designs down, we're going to take statistical analysis. We're going to do statistical analysis on the results so we can figure out which model was the most efficient, which was the most effective. From there, we wanted to build a large-scale model, test in situations like real-world situations, like combat situations, to develop and improve the design so it can be used by naval forces, which is what it was designed for, originally designed for. All right, so we have a video here. Ignore the weird face up there. I'm so sorry. It's horrible. Okay, so what we have here is a very powerful electromagnet. This bottom part right here that I'm moving right now is a series of coils wrapped around an iron center. Now, when current is passed through the coil, it creates a very powerful magnetic field. They stack on top of each other, creating a very powerful electromagnet. When I turn it on, the ring will go flying in the air. Now, the ring goes flying in the air because the magnetic field created by the electromagnet induces a current inside the ring, solid ring. Induces a current inside the ring. Now, this current is flowing in the same direction as the current in the electromagnet, creating the exact same magnetic field. Again, these like fields collide and repel each other, sending the ring again into the air. Now, if we leave it on, it'll see it float. So not exactly here. And then also not quite as loud. When you put it down, it collides with the top of the rail. Too much fun. And then it gets really hot. But that is the general idea.
Here we have our initial model for the coil gun. We have 30-gauge magnetic wire wrapped around a plastic straw, and from end to end, the coil here is about 4 inches, and the straw itself is roughly 6 inches long. And the projectile we used for this was copper PVC, and we also had copper plate steel weave. And the circuit we used for this coil was 2 330-volt 800 microfarad capacitors that we used to charge and discharge to.
Hello. And here's the second model of our coil gun. We started out with this 1-inch single stage down here. It's the same gauge of wire, but it's wrapped in 2 layers. And that works well enough to project the beam out the other end of the barrel. So then we moved on. We added had 4 more one single stages with space in between. So the timing was off on those, so they didn't propel the BB out the edge of the barrel.
Alright, so these are the power methods we used for the railgun initially. Up here you can see two 330-volt capacitors, 800 microfarads each. They are put in parallel circuit. When they are put in parallel circuit, the microfarads add together, creating basically one solid 330-volt capacitor with 1600 microfarads. This is what we use to charge the capacitors. It is a 50-volt, 500-volt DC power source. It can go anywhere from 50 to 500 volts.
Alright, and here is our final model for the coil gun. What we have here is medium gauge magnetic wire wrapped around carbon fiber tube, and we have 6 layers of this. And we have a steel nail for the projectile. The reason we nail this side is because it's much larger, so it's more reactive to the magnetic field. And for our power system, we actually use 24-volt AC power source and a manual switch. The reason we use that as a capacitor is because the capacitor was discharged too quickly, and we need a longer delay just so the nail came to the coil before it actually goes all the way down to the barrel. As you can see here, that when the loop flips, the nail immediately moves down to the center of the coil, and then the current turned off and keeps going all the way out.
So here's the final model of our railgun. Right here we have 2 6-inch by 1.5-inch by 1/4-inch aluminum plates, bolted to the service plate as a rail. And we tried 3 models of this actually. We tried one with the BB sitting on top, and when we discharged the capacitor through it, it jumped off the rail actually because of the forces. And yeah, and then we tried another model with the BB inside the rail, and that didn't BB to the rail, so we saw no movement. Then we tried with this electrogel from the biology department to try and lubricate the rails but maintain conductivity. And that actually, it boils when we ran a constant current through it, but with a pulse, it actually needs to be a small distance, like a few millimeters. Here's the capacitor we use. It's a 450-volt, 480 microfarad capacitor, and we charged it to 200 volts. And here are the zinc-plated steel BBs we use.
Alright, so this was an initial test for the railgun model. As you can see, we have the DC power source hooked up to a 450-volt, 480 microfarad capacitor. From there, you can't quite see a status screen right now, but the wires connect to a railgun with a switch, so that we don't electrocute ourselves, so we can charge the capacitor. Here, we're getting ready to turn it on. The dial is set to 200 volts, so I don't want to be exact, but it's charging the capacitor. Now, the capacitor is charged, we're turning off the DC power source and flipping the switch. The current passes through and propels the BB up into the air. It is showing the design, creating a singe mark though from the arc between the BB and the rail. And then as the BB lands, it creates another spark, just completely discharging the capacitor.
Here we have actually the same video slowed down. And you can see when the switch flips, it makes a big arc right here. It discharges all that current. And when it actually comes back on top of the rails, there's still a start built up in the capacitor.
Here's the still frame of the initial arc, and it's so powerful that it actually screws up the camera. And here's a still frame of the second arc, and you can see it moves a couple millimeters.
Alright, so our conclusion. Well, we like to say we have no solid conclusion. We did have results, but they were not significant. We saw movement. There was some force, but the amounts were not significant enough to simple analysis figure out which one was the most efficient. We would obviously like to continue this experiment with more money, more resources, more time. With a larger capacitor, you saw it created power, but it didn't create enough to move the BB or the nail fire forward. So we'd like to create a larger, or get a larger, capacitor, and then move different designs of the barrels to one complete circuit, so they're uniform. From there, we would like to create further development, so make the railgun with less friction, design it with less friction, and create an actual coil gun that works with multiple stages. With these designs in hand, they could have military potential, as I mentioned in the beginning.
Alright, and here's the actual Navy railgun, and right here is actually part of the Carnet, which is a cement metal barrier, and behind this wall here is actually the railgun. And the seat of the technical that is Block 7. And right here is our actual target. And you can see here we go, here's the projectile actually flying through the target. The flames behind the projectile are not propellant, it's actually just the air burning behind some friction.
And here's actually, that's the initial projectile that was used again. And here's what they got out of it. These are roughly 5.5 inches across. And here's the hole bored through the cement and steel.
Just as a side note, that railgun continues on for another couple meters. It's huge. So what we learned, well, we learned several things. For myself, this is my first time in an actual research environment, so I learned a lot on how to design and conduct an experiment. I'm sure they did as well. We learned the principles behind magnetic propulsion, how they work, how they affect what we design. We learned problem-solving skills. Obviously, lots of our initial designs did not exactly work how we wanted them to. We had to figure out why they didn't work and what to do, solve them. We learned that we also gained more from our failures than we do our success. We learned more from the failed designs than we did from the material that was successful. And we also learned lots of engineering and electrical skills.
We'd like to acknowledge our sponsors. My sponsor for my stay here is the Calgary Clark Western Foundation, and without them I couldn't do the SFI. And my research sponsor is the Bacon Gun, and I'd like to thank them for making this research possible.
My sponsor is the Adolf Coolers Foundation. They sponsored both my stay here and my research project, neither of which I could have done without them.
And my sponsor is the Excel Energy Foundation, which sponsors my research, and a friend Gloria Wall Foundation, which sponsors my stay here at Aspen.
And we'd like to thank the University of Northern Colorado and the Friendship and Faculty School.
We'd also like to thank our mentors, Dr. Matthew Sunak, Maurice Woods III,
Lyle Kingsley, and Nick Gordon.
And of course, we'd like to thank Lord for directing this presentation.
Questions? Akshay? Number one would be to increase the capacity. Oh, yeah, sorry. So if we were to continue, the question was, if we were to continue our research, how would we improve the coil gun and the rail gun? Initially, for both, we would increase the capacitance. We either had enough power to propel the projectile any sort of distance, as you saw. Second, for the coil gun, we would make several stages and use transistors in between so that we could time them correctly and propel the projectile a little farther. For the railgun, we need to create less friction on the rail, but be kept. With creating so much friction on the side of the rail that would solder itself to the rails. That would be the next thing on the railgun.
Yeah. What kind of velocities are anticipated from a large-scale project such as one the United States Navy is working on?
The question was what's the velocity anticipated from another scale, like Navy railgun and stuff. And the velocity for the test shot we saw was actually Mach 7. And
Or some projectile.
it was a 40-pound projectile, and it had the capability to go over 100 miles.
And the energy they used for it was 32 megajoules, and they actually wanted to actually be up to 64 megajoules. Their predicted energy also.
For a full-scale railgun, if you need to charge it, you use a lot of electricity. Do you think that could be a problem because you have not having to do the tires and so in traditional warhead?
Well, the question was, for a full-size railgun that uses a lot of power, would it be slow fire rate because it's well charged. Well, the capacitors actually charge very quickly. What slows them down is the resistance of the wire and what capacitance they have. And so, yes, the full-size program would be slow to charge, but actually charging and discharging time is very quickly. So it charges just about as fast as discharges is.
Do you know how they control the recoil on the railgun? Because what is something that is how to protect the sound velocity and that actually how the large recoil?
Well, the question was, how do they control the recoil from the railgun? With that much power, yes, there's a lot of recoil, and it didn't show in the picture we had, but there are lines of wheels all along the railgun, as well as springs on the side to control the recoil. But the recoil isn't the problem. It's the fact that as the projectile moves forward, all the pressure is put on the rail, and they split apart. That is the problem they're trying to correct themselves.
Do you think that we could eventually get to the point where we can railgun?
There are already the question was if we could ever get to the point of handheld railguns. And there are several handheld railguns right now. There are even handheld coil guns.
With enough velocity to...
Yes. They travel faster and farther than bullets.
A lot of
traditional. Oh yes, Colt 49 made in Germany. Actually sells. It's a linear accelerator coil gun. It fires faster than the traditional combustion gun, combustible gun. I don't know.
So this is the railroad road is still part. Is there signal plumbing programs?
The question was, is there a similar problem with the railgun, or with the coil gun, with the rail splitting apart? And actually, it's the opposite. The coils tend to compact. That's why with the first bale model we did of the rail or the coil gun, it actually compressed the straw so we couldn't fire it.
So, they actually, there's so much resistance in the wire, heat of the wire. That's another factor that, for the coil guns, disadvantage.